Everybody, today I'm going to show you a little bit about drawing Lewis structures for covalent compounds. There's a series of rules for drawing Lewis structures for covalent compounds. I like to break them down into 5 steps. Step 1, calculate the total number of valence electrons or dots you can draw given the formula of the compound. Step 2, draw the skeletal structure. This includes identifying what goes in the center of the structure, which will be the least electronegative atom. Reminder that hydrogen can never go in the center, it's terminal. And once you've identified and drawn the skeletal structure, it involves connecting each atom with a single bond. Step 3, you're going to distribute the rest of the electrons with the goal of giving the atoms an octet or duet as appropriate. You're going to complete the octets of terminal atoms first, and remember that internal atoms are the only atoms that can violate the octet rule, either by having an expanded octet or an incomplete octet if it's boron or beryllium. We'll only look at the expanded octet in this video. If you run out of electrons that you can draw based on your calculation in step 1, and not everything has an octet, then you're going to need to use double and triple bonds. And once you think you have the appropriate structure, it is useful to use formal charge to check to make sure that you have the optimal structure. That'll be the structure where all atoms have the lowest possible formal charge. And it is possible to have multiple structures with equivalent formal charges, making those structures equivalent. We call those resonance structures. We're going to look at 4 examples today, the first of which is N2H4. N2H4 has a total of 12 valence electrons. Skeletal structure, H is going to go on the outside with 2 N atoms in the interior because N is the least electronegative of the group and H has to be terminal. The 12 valence electrons, we arrived at that 5 from each nitrogen and 1 from each hydrogen. Going to connect each atom in the structure with a single bond. That's going to use 6 of our 12 electrons, leaving 6 more. Nitrogen, each nitrogen that remains or that is in the molecule requires a minimum of 4 more electrons to have an octet. That's 4 times 2 or 8. So what we know is we're going to have to form a double or triple bond to give everything an octet here. So let's try a double bond. If we're going to form a double bond, we'll put it between the 2 nitrogens. That means that we have used 8 electrons. We have 4 left. And coincidentally, each nitrogen needs 2 more. So we'll put a lone pair on each nitrogen. And in this structure, everything now has an octet. There's no reason to check formal charge here, as none of these elements can have an expanded octet because they are not in period 3 or lower on the periodic table. So there is no other way to draw a stable structure of this compound. Let's switch to KrCl2, Krypton I Chloride. Chlorine has 7 valence electrons. 7 times 2 is 14, plus 8 is 22. So we have 22 valence electrons. Chlorine is going to be on the exterior here because krypton has an electronegativity of 0. We're going to connect those 2 atoms, or the 3 atoms. That costs us 4 electrons. We're down to 18. We're going to give each chlorine an octet. That's going to cost us an additional 12 electrons. So we have used a total of 12, 13, 14, 15, 16 electrons. We have 6 more electrons remaining. Krypton requires 4 of those 6 electrons to complete its octet. We have 2 electrons that remain, and everything has an octet. We can't just ignore them. We also can't put them on terminal atoms because they can't violate the octet rule. So this molecule is going to have an expanded octet with krypton in the middle. So that extra pair of electrons is going to go on krypton for a total of 10 electrons surrounding krypton. Again, here, there's not really any reason to calculate formal charge. The only atom that might violate the octet rule further is krypton, and there's just no reason for any double or triple bonds to form between it and chlorine because it's already got an expanded octet, so we won't bother to calculate formal charge here. We have pretty good confidence we have the correct structure. Let's look at our last two examples. HCO2 is the first of those examples, and that has 18 valence electrons, 1 from hydrogen, 4 from carbon, 12 from oxygen, 6 times 2, and 1 from the -1 charge. In our skeletal structure, this is an ion, so we'll start with a bracket. We'll put H on the left. Carbon has to go in the middle. Put an oxygen above it, an oxygen to the right of it, close bracket, and a -1 charge. Connecting everything with a single bond. We've used 6 of our 18 electrons. We have 12 more. Well, that's good because we have 2 oxygens that need 6 electrons apiece. We'll put 6 electrons around the right oxygen, and then we'll pause for a moment as I evaluate, should I put those other 6 electrons around the top oxygen? The answer seems from an octet rule for that oxygen to be yes. The problem is, if I do that, the carbon will not have an octet. So instead of putting all 6 of those electrons around oxygen on the top, I'm going to form a double bond and then put the remaining 4 electrons around oxygen. That gives everything in the structure an octet or duet and uses 18 valence electrons. A note here, you notice there are 2 oxygens. Why did I put the double bond on the top oxygen? Well, because I chose to. But I could just as easily put it on the right oxygen. Let me draw that for you. Same structure as on top, except we move the double bond to the right oxygen, the single bond to the top oxygen. Still, everything has an octet, still 18 electrons. So which structure is better? To understand that, we have to calculate the formal charge of each atom. Let's start with hydrogen. It has 1 valence electron. It has 0 lone pair electrons. It forms 1 bond. It has 2 electrons, and half of that is 1 for a formal charge of 0. Noting that on each structure. Let's then go to carbon. 4 valence electrons. Again, no lone pair electrons. 4 bonds with 8 electrons, half of 8 is 4, for a 0 formal charge. There's 2 types of oxygens. There's the single bonded oxygen, or SO, and there's the double bonded oxygen, or what we'll call here DO. Okay? SO, 6 valence electrons. The single bonded oxygen has 6 lone pair electrons. It has 2 bonding electrons. Half of 2 is 1 for 7, or a -1 formal charge. Noting that on both structures because it's equivalent in both places. Double bonded oxygen, 6 valence electrons, -4 lone pair electrons. It has 2 bonds, which is 4 electrons. Half of 4 is 2, so +2. And 6 minus 4 plus 2 is 0, so it has a 0 formal charge. You'll note the formal charge on both structures is equivalent, and I'll draw this double-headed arrow between them to indicate that these 2 structures are equivalent or resonance structures. The actual structure is the hybrid between them. The last molecule is CO2. Carbon has 4 valence electrons, each oxygen 6. 6 times 2 is 12, plus 4 is 16 valence electrons. Carbon is going to have to go in the middle. And in this structure, if we connect both the carbon to both oxygens, we use 4 electrons. There are 12 remaining. If I put the 12 remaining around oxygens to give them an octet, carbon will not have an octet, which means we're going to have to use double or triple bonds. I'm going to use a double bond. And if I do that, I'm going to do it on both sides because then carbon will have an octet, and that will leave me with 8 electrons, 4 for each oxygen, meaning everything follows the octet rule. Okay? Turns out, however, that there is an equivalent way to draw, or a different way to draw this structure. And that is, instead of using a double bond on both sides, I can use a single bond and a triple bond. If I do that, the oxygen on the right with the triple bond gets 1 lone pair of electrons. The oxygen on the left with the single bond gets 6 lone pair electrons. If we run through and calculate the formal charge here on these structures, carbon in both structures has a formal charge of 0. Let's go up to the top structure with the 2 double bonds. The oxygen on the right, 6 valence electrons minus 4 valence electrons, or 4 lone pair electrons plus 2 bonding electrons, which is half of the 4 bonding it has, gives it a formal charge of 0, which means the one on the right will also have a formal charge of 0. I could go to the bottom structure and calculate the formal charge on each oxygen, but it's no way going to be lower than 0, which is what it is now on every element in the top structure, which means the top structure is the preferred structure. I hope you've learned a little bit about Lewis structures today, and I hope you'll do a bunch of practice, which is the only way to get to be at the expert level of drawing Lewis structures of covalent compounds. I look forward to seeing you again in a future video.